Welcome to this comprehensive scientific lecture on personalized diet and cooking systems powered by artificial intelligence. Over the next 16 minutes, we'll explore how AI adapts recipes based on individual metabolism, health data, cultural background, and personal preferences. We're living through a revolution in nutrition science. For decades, dietary guidelines have been one-size-fits-all, but recent research shows that individuals respond differently to the same foods. Consider two individuals eating identical meals. Person A might have a moderate blood glucose response, while person B experiences a dramatic spike. This metabolic diversity is why personalized nutrition is so crucial. Let's break down how AI creates personalized diet and cooking systems. The framework consists of four main data integration layers. The AI core integrates metabolic data, health records, cultural context, and personal preferences. Each layer feeds critical information that shapes recipe adaptation. Let's dive deep into metabolic profiling. This is perhaps the most scientifically rigorous component of personalized nutrition. Continuous glucose monitors provide real-time data on how your body responds to different foods. This data stream shows significant variability throughout the day. Research shows that basal metabolic rate can vary by 25 to 30% between individuals of the same age, weight, and gender. This variation is enormous. The Harris-Benedict equation estimates basal metabolic rate using weight in kilograms, height in centimeters, and age. But this is just a population average. AI systems don't rely on population averages. They measure your actual metabolic response through continuous monitoring and machine learning algorithms. Here we see two different glucose response curves. The blue curve shows a healthy, moderate response. The red curve shows a more problematic spike and crash pattern. Understanding insulin response is critical. When blood glucose rises, your pancreas secretes insulin to move glucose into cells. When glucose enters the bloodstream, the pancreas detects this rise and releases insulin. Insulin acts as a key that unlocks cells, allowing glucose to enter. Insulin sensitivity is not uniform across populations. Some individuals are highly insulin sensitive, while others show insulin resistance. The HOMA-IR index quantifies insulin resistance. It's calculated by multiplying fasting glucose in milligrams per deciliter by fasting insulin in microunits per milliliter, then dividing by 405. AI systems learn your personal insulin sensitivity pattern over weeks and months of data collection. This allows for incredibly precise dietary recommendations. Let me give you a concrete example called the potato paradox. This comes from a landmark study published in the journal Cell. In a study of 800 individuals, researchers found that some people had minimal glucose response to potatoes, while others experienced dramatic spikes. Same food, opposite metabolic effects. The study tracked 800 people for 1 week, monitoring their glucose response to over 46,000 meals. The variation was extraordinary. The researchers found that gut microbiome composition explained much of this metabolic variation. Different bacterial populations process carbohydrates differently. The gut microbiome is like a complex ecosystem. Each colored circle represents different bacterial species. This ecosystem profoundly influences how you metabolize food. Now let's examine how AI integrates clinical health data. This layer incorporates medical conditions, medications, and biomarkers. The AI recipe adapter receives inputs from various health conditions. If you have diabetes, it reduces simple carbohydrates. For hypertension, it limits sodium. For high cholesterol, it adjusts saturated fat. Let's work through a detailed example for type 2 diabetes management. This is one of the most common applications of personalized nutrition AI. For type 2 diabetes, the primary goal is maintaining blood glucose between 80 and 130 milligrams per deciliter before meals and below 180 after meals. This diagram shows the target glucose range in green. Values below 80 risk hypoglycemia, shown in red on the left. Values above 130 indicate hyperglycemia, shown in red on the right. The AI calculates glycemic load for each component of a recipe. Glycemic load accounts for both the quality and quantity of carbohydrates. Glycemic load equals glycemic index times grams of carbohydrates divided by 100. This gives a more accurate picture than glycemic index alone. Let's see how AI adapts a traditional pasta recipe for a diabetic individual. This will show the practical application of these principles. The original recipe has 200 grams of pasta with a glycemic load of 35, which is too high. The AI version cuts pasta in half, adds zucchini noodles for volume, and switches to turkey for lower saturated fat. The new glycemic load is 18, much better for glucose control. The AI also accounts for medication interactions. For example, if someone takes metformin, the system might increase fiber content to enhance the drug's effectiveness. Cultural context is crucial for adherence. People are far more likely to follow dietary recommendations that respect their cultural food traditions. The AI system is trained on recipe databases from dozens of cultures. It understands the fundamental flavor profiles, cooking techniques, and ingredient combinations that define each cuisine. Let me show you how AI adapts Indian cuisine for cardiovascular health while preserving authentic flavors. The traditional butter chicken uses heavy cream and large amounts of ghee, resulting in 45 grams of saturated fat. The AI adaptation uses yogurt instead of cream, reduces ghee significantly, substitutes olive oil, and swaps white rice for brown rice. Saturated fat drops to 12 grams while maintaining authentic spice profiles. Crucially, the spice profiles remain identical. The AI preserves the garam, masala, turmeric, cumin, and coriander ratios that define the dish's authentic flavor. AI systems learn that certain cultural food combinations provide complete nutrition. For example, rice and beans in Latin cuisine create complete proteins. The fourth layer incorporates individual preferences and constraints like allergies, food dislikes, ethical choices, and budget limitations. All preference constraints feed into the final recipe generation. The A. I must satisfy metabolic needs, health requirements, cultural authenticity, and personal preferences simultaneously. This is a constraint satisfaction problem. The A. I must find recipes that satisfy dozens of simultaneous constraints while optimizing for taste and nutrition. Let's examine how the AI actually generates recipes. This involves sophisticated machine learning techniques. The AI uses a neural network architecture. Input nodes represent user features like metabolic rate, health conditions, and preferences. Hidden layers learn complex patterns. Output nodes generate recipe components and cooking instructions. The system is trained on millions of recipe outcome pairs. Each training example links a recipe to actual measured metabolic outcomes from real users. The AI uses reinforcement learning. When a suggested recipe produces good glucose responses, that pathway is reinforced. Poor outcomes lead to parameter adjustments. Let me walk you through a real-world example to tie everything together. Meet Sarah, a 42-year-old woman with prediabetes and a busy work schedule. Sarah has prediabetes with fasting glucose of 110 milligrams per deciliter. She also has elevated LDL cholesterol at 145 milligrams per deciliter. She works long hours and needs quick meal solutions. In week 1, Sarah wears a continuous glucose monitor and logs her normal eating patterns. The AI establishes her baseline metabolic response to various foods. Her baseline data shows significant glucose variability, with several spikes above 140 milligrams per deciliter. The AI identifies breakfast and dinner as particularly problematic meals. The AI identifies that Sarah's morning cereal routine causes a 50-point glucose spike within 30 minutes. Her insulin response is sluggish. In week 2, the AI begins making targeted recipe suggestions based on her metabolic profile. The AI replaces her high-carb cereal breakfast with Greek yogurt, berries, and almonds. This reduces carbohydrates from 75 grams to 25 grams while increasing protein and healthy fats. After implementing this change, Sarah's morning glucose spike drops from 50 points to just 15 points. Her energy levels are more stable throughout the morning. For dinner, Sarah loves Italian food from her family heritage. The A. I must adapt these recipes while preserving their cultural authenticity. The AI adapts her family lasagna recipe by replacing pasta layers with thinly sliced zucchini. It uses part-skim ricotta and ground turkey. The glycemic load drops from 28 to 11, a dramatic improvement. Remarkably, when Sarah served this adapted version to her family, they couldn't tell the difference. The flavor profile remained authentic. By week 8, Sarah shows measurable improvements across multiple health markers. Her fasting glucose drops from 110 to 95 milligrams per deciliter, moving out of the pre-diabetic range. LDL cholesterol decreases from 145 to 125. She loses 10 pounds and reports significantly improved energy levels. Let's discuss the economics and scalability of personalized nutrition AI systems. These are critical factors for widespread adoption. A comprehensive analysis of the cost structure reveals interesting economics. The continuous glucose monitor is the largest cost at $75 per month. AI processing costs about $8. Support staff and infrastructure add $17. Total cost is approximately $100 per month per user. However, consider the alternative costs. Type 2 diabetes management averages $9,000 per year. Cardiovascular disease treatment can exceed $20,000 annually. Personalized nutrition prevention costs $200 per year. Disease treatment costs exceed $9,000 per year. The prevention approach is 7.5 times cheaper. Scalability improves dramatically through semiconductor advances. Next-generation glucose sensors will cost under $20 per month. Looking forward, AI nutrition systems will become increasingly predictive and preventative. Future systems will integrate genomics, proteomics, metabolomics, and microbiome analysis. This multiomics approach enables prediction of disease risk decades before symptoms appear. Certain genetic variants predict how you metabolize specific nutrients. For example, the MTHFR gene affects folate processing. Consider caffeine metabolism as a concrete example of genetic personalization. The CYP1A2 gene controls caffeine metabolism. Fast metabolizers clear caffeine quickly, and coffee consumption reduces cardiovascular risk. Slow metabolizers clear caffeine slowly, and coffee consumption increases cardiovascular risk. AI systems will adjust recipes based on your genetic profile. Slow caffeine metabolizers receive recipes without coffee or limit intake to morning hours. Future systems will also integrate environmental sensors to provide real-time adaptations. Environmental factors like air quality, pollen count, temperature, and stress levels will trigger recipe adaptations. High stress might increase magnesium-rich foods. Poor air quality could boost antioxidant recommendations. We must address ethical considerations and data privacy concerns. These systems collect incredibly sensitive health information. Health data is among the most sensitive categories of personal information. Glucose levels, genetic variants, and medical conditions must be protected rigorously. Best practices include encrypted storage, de-identified processing, and user control. Data should be encrypted both in transit and at rest. Processing should use anonymized identifiers. Users must have the right to delete all their data at any time. There are legitimate concerns about insurance discrimination. Could insurers use this data to deny coverage or raise premiums? Strong legal protections are essential. The Genetic Information Non-Discrimination Act in the U.S. is a start, but needs expansion to cover all health data. Scientific validation, through rigorous clinical trials, is critical for establishing efficacy. Several randomized controlled trials have now been published demonstrating the effectiveness of AI personalized nutrition. The PREDICT study with 1,000 participants demonstrated huge inter-individual variation in metabolic responses. The Personalized Responses study with 800 participants showed AI recommendations improve glycemic control by 28% compared to standard dietary advice. The effect sizes are substantially larger than traditional one-size-fits-all dietary interventions. Traditional diets show 10 to 15% improvement, while personalized AI approaches show 25 to 35% improvement. Despite the promise, there are significant implementation challenges to address. Cost remains a barrier. At $100 per month, many people cannot afford personalized AI nutrition systems. Digital literacy is required. Users must be comfortable with smartphone apps, data tracking, and interpreting AI recommendations. Integration with existing healthcare systems is complex. Electronic health records must be able to share data securely with AI nutrition platforms. We need to move from the current fragmented state to a future integrated state where AI nutrition systems seamlessly connect with doctor visits, lab results, prescriptions, and fitness tracking. Let's do a back-of-envelope calculation to estimate the potential population health impact of widespread AI personalized nutrition adoption. The U.S. adult population is approximately 260 million people. Current prediabetes prevalence is 38%, affecting about 100 million Americans. Without intervention, approximately 10% of prediabetics progress to type 2 diabetes each year. That's 10 million new cases annually. If AI personalized nutrition reduces this progression rate by 50%, that prevents 5 million new diabetes cases per year. Each diabetes case costs about $9,000 per year to manage. 5 million prevented cases saves $45 billion annually in healthcare costs. This calculation doesn't even account for improved quality of life, increased productivity, and reduced complications like kidney disease and amputations. Current annual diabetes costs are $327 billion. With widespread AI personalized nutrition, this could decrease to $282 billion, a savings of $45 billion per year. Smart kitchen devices will amplify the impact of AI nutrition systems by automating recipe execution. Smart ovens automatically adjust temperature and timing. Smart scales precisely measure ingredients. Smart blenders follow AI-generated smoothie recipes. These devices execute personalized recipes with minimal user effort. Automated portion control is particularly powerful. The devices measure exact amounts specified by the AI, preventing the common problem of portion size errors. AI systems also optimize cooking techniques to maximize nutrient retention. Boiling can result in significant nutrient loss, steaming preserves nutrients better, and AI systems will choose the best cooking method for each ingredient.